let's say we had to calculate something like. Let's try that. The integral from 1 to e squared of x cubed natural log of x dx. Okay, so I see a mixture. I'm thinking either u sub, integration by parts. Could it be a u sub? Probably not. There's not really great choices for you here. Well, I mean, there's perfectly fine choices for you. They're just not going to result in what we want. You can pick u equal to x cubed, but du being 3x squared isn't looking promising. You can pick u equal to the natural log of x, but du being 1 over x dx, also not looking very promising. So you could write more stuff down there, but we're going to go the path that is the sensible path, which is doing an integration by parts. Meaning we're trying to pick u equal to, in this case, what?
ln.
Yeah, the natural log of x. So we're going to let u equal the natural log of x. And we're just going to say that dv is all the rest. X cubed times dx. And then we write down all the things. Our du is 1 over x dx. Our v is the antiderivative of x cubed, which is x to the 4th over 4. And then we rewrite it. Now, here's what I would suggest for this one. I'm going to do the indefinite integral first, meaning I'm just going to say the integral of x cubed natural log of x dx is equal to u times v, so natural log of x times x to the 4th over 4, minus the integral of v du, x to the 4th over 4, plus u times 1 over x dx. This is kind of exemplifying more what I was talking about last time, where I don't really want to write the limits of integration here, and write them here, and write them here. So I'm just going to do the integral first, and then at the very end, you'll see what I mean. So we still need to simplify and integrate this. So with the natural log of x times x to the 4th over 4 minus, I'm going to bring the 1/4 out. I'm left with an x to the 4th over x, which simplifies to x cubed. Now we're going to integrate. And we're going to get the natural log of x times x to the 4th over 4 minus 1/4 times the integral of x cubed is x to the 4th over 4. You could put a plus c in there if you felt like you needed to, but since we're doing a definite integral, and this is kind of just our in-between work, you don't really need to write that down. So then, what I'm going to do is I'm going to go back and say, okay, well, if the integral of x cubed natural log of x dx is equal to the natural log of x times x to the 4th over 4 minus 1/4 of x to the 4th over 4, then the integral from 1 to e squared of x cubed times the natural log of x dx is equal to all of that, natural log of x times x to the 4th over 4, minus, I'm going to write that as x to the 4th over 16 from 1 to e squared. That's kind of the gist, right? Do all the complicated integration without writing your limits of integration the whole time. And then at the very end, just say, okay, the integral of this function is just equal to its antiderivative, simplified as much as you can, evaluated between your endpoints. And then we're going to plug in. So we're going to get the natural log of e squared times e squared to the 4th over 4 minus e squared to the 4th over 16 minus, now you're going to plug in 1, natural log of 1 is 0 times 1/4 minus 1/16. And we could simplify that if we want to. Natural log of e squared is 2. E squared to the 4th is e to the 8th. Minus e squared to the 4th is e to the 8th over 16. And then minus, that's a 0. So minus and minus is plus 1/16. And sure, you could simplify this further if you really wanted to, but it's not really necessary. Yeah.
Do you have any idea if we could possibly lose points for not putting the limits along the way in our work?
That's a question you would have to ask your teacher. I don't think you should, as long as you're clear with what you're doing. Right? I think what we've written here is very clear. I've written the indefinite integral, and I found the indefinite integral. I might put a plus c here just to be extra careful then. And then I'm saying, okay, well, if that's that, then that's that. I've as far as I'm concerned, that should be totally fine, but people have different ideas about things. So yeah. it's certainly kind of a pain in the butt to write the limits of integration along the way, because you have to kind of write them, you have to write them here and here. So if you were, no, I don't really want to do that. Yeah, I could, I don't want to. So, and you don't really, I don't think you need to. Other questions about this one? Yeah. That's a 0. Yeah, sorry. That's a natural log of 1 is just going away because it's 0. My pen was just, I keep trying to tell myself it's throw away these pens. They're almost out of ink, but they also have a little bit of ink in them, so I keep using them. Yeah. I feel like one of these is still okay. Maybe, maybe not. Let's see. You two are trash. You two might be okay. Yeah, really, I should just, there's no trash cans. Here's the problem. We keep going to throw away a pen and then there's nowhere to throw it away to. So I'll put it back there. Anyway, I'll just leave them there. Maybe. Other questions about this one? Okay. Me too. Let's see. I had a couple other fun examples here. Oh, I know what we should do. We should do one like that. Yeah, let's do a couple more. So, sorry, I have to think about. Sure. So let's say we have something like, sure, this one's just kind of interesting. The integral of cosine of the natural log of x dx. Which you could probably see maybe either way. In fact, if for me, honestly, I would probably see this as a U substitution with a back sub. That's how I would probably see this, but you can kind of go either way. So let me show you what I mean. You could say, I'm going to do a U sub, and there's only really good one choice for you if you're doing a U sub. You're going to let U equal the stuff stuck inside another function. I don't love my du options here, right? If du is 1 over x dx, and if you want to do this thing where you solve for dx, that's going to be, it could be fine. X du, that seems problematic because the x isn't going to cancel out. It is a problem. We're gonna deal with it. So I don't know what your teacher has said about back substitution specifically. Instead of doing this, I prefer to do this, where you say, well, if I know something's going to be a problem, I'm still going to try and do a back sub. I'm going to take this and I'm going to solve for x. So e to the u is equal to x. And if we differentiate both sides, the derivative of e to the u is e to the u du. The derivative of x is dx. Now, what I want to point out is whether you see it this way or you see it this way, you're going to end up at the same place, because what's x equal to? Right. Well, that's literally the same thing we had before right there. So you can get there either way, either by solving for x first and differentiating both sides, or differentiating both sides and then kind of solving for dx and then replacing x with whatever it's equal to. I feel like this is easier to, what's the word, to execute. This is definitely easier to do if you're just solving for x and differentiating both sides. This requires a little more, I don't know, you have to be more observational here, because yeah, you can see that dx equals x du, but then also noticing that x is equal to e to the u, you have to be like, oh, I need to solve for x. So I feel like it's harder to do it that way personally. In either case, this is going to become the integral of, so cosine of u, and then the integral, or sorry, and then dx is equal to e to the u du. So here's what I'd point out. If I did a U substitution and saw that it got me not only just to an integration by parts problem, but a kind of terrible integration by parts problem, because this is one of those things where you have to do integration by parts twice, and then you get back the same thing you started with, and you have to bring it over to the other side and divide by 2. It probably would have just been easier to do integration by parts from the get-go. Sometimes you'll certainly do a U sub and then have to do integration afterwards. This is not the case. Here's just a, this is terrible no matter which way I go. So it's probably going to be better just to do the terrible thing first. So instead of doing this, even though this would work, it'd be a pain. Instead, let's just see what happens if we do integration by parts from the get-go. So that said, if we're doing integration by parts from the get-go, you can't do functions of functions when you're doing integration by parts. You can't, so like, for example, if I'm doing integration by parts, I can't do something like, I don't even want to say this because it sounds so wrong to me, but you can't like let u equal the natural log and dv be cosine dx, because you don't have cosine x dx, you have cosine of the natural log of x. So integration by parts, you can't really do like a function of a function. There is no composition that really works. You have to let u equal cosine of natural log of x. There's no other real choice to make for u. It's kind of weird. It's a weird problem. I'm not gonna lie. This is a weird problem. I don't know. I think it's worthwhile, but we'll see. So u kind of has to be the whole shebang. And then if you use the whole shebang, dv is just the tiny little rest dx. du, okay, derivative cosine of some stuff is negative sine of the stuff times the derivative of the stuff, which is 1 over x. And v is going to be just x. Then we rewrite the thing. So the integral of cosine of natural log of x dx is going to equal uv, so x times cosine of natural log of x, minus the integral of v times du. Now let's be thoughtful before we do this too much. If I multiply v times du, or x times negative sine of natural log of x times 1 over x, what's going to cancel?
The 1 over x.
Yeah, the 1 over x and the x. So, I mean, we could write it. I could write negative sine of natural log of x times 1 over x times the x times the dx. I probably should have written the x first, but I wanted them to be next to each other. These cancel. Also, that becomes a plus. And I do think it's worth making that simplification along the way. This is going to equal x times cosine of the natural log of x plus the integral of sine of the natural log of x dx. And now what I hope you see is that we're essentially back where we started, or close to where we started. We pretty much have the same type of integral. Sine and cosine are virtually the same function. I mean, they're not exactly the same, but they're the same enough that if you see sine of something versus cosine of something, you should think, oh, those are really the same integral. I mean, they require the same amount of work. So we're back to kind of where we started, meaning we're going to do the process again. Just like, and I know it's been a whole weekend since we talked about it, just like last weekend when we were doing like the terrible e to the something times sine of something, and we had to do it twice, and we got back to where we started. After we did the first integration by parts, we saw essentially the same kind of integral again. We got an e to the something times either sine or cosine. So if you see kind of just sine switching for cosine or cosine switching for sine, it probably means you're in a do it twice situation, end up with what you started, subtract it or add it over to the other side, and then divide by 2 kind of thing. I know that's very like this kind of thing, right? I'm seeing like 5 steps, but it's really kind of a process that you see semi-regularly. So let's continue. We're going to do the same sort of thing. We're going to let now, for sine of natural log of x, we're going to let u equal sine of natural log of x. And the dv is still dx. And the du is, the derivative sine of stuff is cosine of natural log of x times 1 over x dx. And the v is going to be x. So writing it now, I've got the integral of cosine of natural log of x dx equal to x times cosine of the natural log of x plus the integral of this. So again, ultraviolet super voodoo, ultraviolet, so x times sine of natural log of x minus the integral of voodoo, v du, so x times cosine of natural log of x times 1 over x dx. And just like before, the x and the 1 over x cancel out. And now look, I'm back to actually where I started. I have, again, the integral of cosine of natural log of x dx. And that's where you don't keep going. We add it to both sides. And whatever, here we happen to have a nice, like we just add 1 of it to both sides. So I'm going to add the integral of cosine of natural log of x dx to both sides. If you add something to itself, you just have twice of it. So I'm going to have 2 times the integral of cosine of natural log of x dx equal to x cosine of natural log of x plus x sine of natural log of x. And then finally divide both sides by 2. So you end up getting the integral of cosine of natural log of x dx equals all of that divided by 2, or times 1/2. 1/2 times x cosine of natural log of x plus x sine of natural log of x plus c. Kind of crazy. I feel like this is an example teachers sometimes like to go to because it's kind of the only other relatively straightforward example of this doing it twice kind of thing and then getting the thing you started with and adding it back over to the other side. There's not a lot of other examples of that other than something like, so this is similar in process to the integral of e to the x times sine of x, or e to the x times cosine of x, where you do the thing twice, you get back what you started. Divided by 2. Kind of a weird problem, but kind of neat. Yeah. Switch that up a little bit. Kind of off here. Just a second. Go the other way. There, that seems closer to being good. Let's see. I feel like I had one other example I wanted to make sure I hit before we go on to the next one. Yeah, let's take an example too. Sure, let's do one more. Let's say we had, yeah. Papers, come on, papers. Okay, I guess that you're just the only, I'm sorry, I thought there was more papers. Sorry. So let's say we have something like, sorry, brain. Yeah. The integral of x to the 5th sine of x cubed dx. This is some terrible stuff I would come up with if I was writing a hard test. So this looks awful. I don't see really a good path at all, to be honest. If I'm thinking, so again, I'm thinking it's a mixture. That's the only thing I'm really confident of, is I've got x to a power and I've got a trig function. So I could either try a u sub or I could try integration by parts. Integration by parts is not a good thing to do yet, and here's why. If you were going to try integration by parts, what's the thing we should choose for u? X to the 5th, right? Because you're trying to choose to be, right, I should say, right, I'd be u equal to, I don't have a log, I do have a power of x. So I've got x to the 5th as my power of x. But if I did that, look what happens. If u equals x to the 5th, and du is 5x to the 4th, my dv has to be the rest. And I'm going to tell you all, not only do I not know how to integrate sine of x cubed, I think it's actually impossible. Like some functions cannot be anti-differentiated. They do not have a nice antiderivative. So the whole point, or the whole thing you should be looking for when you're thinking integration by parts, is dv should be at least be able to anti-differentiate. Specifically, it should be relatively straightforward to anti-differentiate. So that seems like it's kind of out of the question. So instead, well, if the thing I was going to try didn't work, I try a different thing. So let's try u sub. So u sub. So the only kind of reasonable choice for you, I think, is letting u equal x cubed. And hopefully I've set this up correctly, so it's going to be fine. Yes, I did. Okay, good. Okay. So u is going to be x cubed. And then my du is 3x squared dx. So my dx is going to be 1/3 times du over x squared. So my dx is equal to, I guess I could put the 3 below the du. I just know it's going to cancel out. So then let's start rewriting this thing. So I'm going to have the integral of, well, I'm going to have an x to the 5th here. And then I'm going to have a sine of u. And then my dx is going to be 1/3 du over x squared. And I can definitely cancel that x because again, you're always trying to make sure that x, that thing below your du, whatever the variable is there, is always needs to cancel out or go away or be replaced somehow. It does. I can definitely say x to the 5th divided by x squared is going to be x cubed. So canceling that and that leaves me with an x cubed. So now I've got 1/3. Let's bring it out in front. I've got x cubed times sine of u du. And now, what's x cubed equal to? U. And this is where if I had been thinking more ahead, I would have used a different variable for my u substitution so that I could still use u and v for my integration by parts. But since I didn't, we're going to use w instead of u. That's typically the choice people make when they're doing integration by parts and they've already used u. You don't want to use u again. You typically always should be using, like it's totally fine if you're doing repeated integration by parts to keep using u and dv because you're just dealing with x. But if u is my variable, I need to make a different choice. So we're going to pick w equal to u, and we're going to pick dv equal to the rest. We're not going to pick, we're forced to pick dv equal to the rest. Our dw is equal to du, and our v is equal to the antiderivative sign, which is negative cosine of u. And so I should point out, we're not going to be writing down ultraviolet super voodoo, right? Instead of, although it'd probably totally be fine, but fine, I'm not still going to be careful. Instead of uv minus the integral of v du, we're going to write wv minus the integral of wd. No, vdw, sorry. And then we're plugging in the u things for each of those. So when I write this down, my integral is going to equal w, which is u, times v, which is negative cosine of u, minus the integral of v, which is negative cosine of u. Yes, I could just make that positive, but I didn't because it wasn't. Because I didn't. And then times dw, which is du. So even though I'm saying the v's and the w's, I'm writing down the variable I actually want, which is the u's. And then we try to make this not terrible. This is going to equal negative u cosine of u, minus and minus is plus. The antiderivative of cosine is positive sine of u plus c. And then, since we did a u sub to start, we have to change back to our original, variable and get negative x cubed times cosine of x cubed plus sine of x cubed plus c. So sometimes you have to do a u sub and then integration by parts. I think that's pretty, yeah, it's pretty much as terrible as they get. All right. Other integration by parts questions before we start talking about some trig stuff? Yeah.
Question 4 on the.
Sure. Question 4. Oh, so I would respond with, it's not an integration by parts question. So here's the thing, and again, I'll say this over and over and over again. Integration is kind of you have to kind of guess. Sometimes I'm guessing sometimes. Like, well, I don't know, try a thing. And so when I look at something like the integral of, I have x to the 6th times e to the x to the 7th, first and foremost, I see a mixture. I see a power of x times an exponential, and e to the x. And so when I see a mixture, I'm really boiling it down. Now, again, right, there could be other ways to go, but 99 times out of 100, especially in this class, if you got a mixture, it's either going to be u sub or integration by parts. And typically we are feeling like, usually, straightforward u sub is typically the easier thing to do. So I'm always going to try the u sub first. So a plausible choice for u is x to the 7th. For all the usual reasons we like to pick u. We're going to get du equal to 7x to the 6th dx. So dx is equal to du divided by 7x to the 6th. And this is going to work out just great. We're going to end up getting x to the 6th times e to the u times du over 7x to the 6th, and the x to the 6th exactly cancel each other out. No, that's not what to do. Go away, go away. So then we're left with 1/7 integral of e to the u du. Do be careful and thoughtful here. You still have to anti-differentiate e to the u. I know I'm going to get e to the u, but I really want you to think, oh, I'm doing a thing. When I go from this step to the next step, I am taking the antiderivative of e to the u, and I'm getting e to the u, and then I'm tacking on a plus constant. And then lastly, I have to go back to the variable I started with since it's an indefinite integral. So u is x to the 7th, so I'm going to get 1/7 e to the x to the 7th. We'll see. And I don't really think you could do this one via integration by parts. There are some weird problems you can do kind of either way that people like to do. I'm not a fan, but there are some, especially with trig stuff, you can do kind of one way or the other, which is weird to me. But other questions from homework 6.2 before we start talking about some trig stuff? It's totally fine. What does the trig stuff do? Okay, sure. I printed these out from a while ago, so it's like, oh, it still says it's due on today. I'm like, that can't be right. Okay. Let's talk about some trig stuff. Trig stuff. Not that there's a ton of problems on the section, that doesn't mean we can't talk about it. So there's a couple kind of, how's that right? There's some rules. That's a bad word. There's some guidelines for dealing with trig stuff when you have something more complicated than just something obvious. So I'm going to kind of remind you all, there's an expectation that we know how to anti-differentiate the following 6 things. You should be able to say that the antiderivative of cosine of x is positive sine of x. The antiderivative of sine of x is negative cosine of x. The antiderivative of secant x tangent x is equal to secant of x. The antiderivative of cosecant x cotangent x is negative cosecant of x. The antiderivative of secant squared x is tangent x. And the antiderivative of cosecant squared x is negative cotangent x. And we know all those because we know how to take derivatives. We know the derivative of secant is secant times tangent, so we know the antiderivative of secant times tangent is secant. And then I'm going to go one step further and say something like the integral of cosine of 6x. I don't want to do a mini u substitution here. I want to just say what the answer is. Yes, we could say u equals 6x, du equals 6dx, divide by 6, you're going to end up getting 1/6. But we can also be like, we know how to do this. This is going to be sine of the same stuff, but then I have to divide by 6. Or if you prefer, say 1/6 times sine of 6x. For the same sort of reason, we've been saying the integral of e to the 4x is 1/4 e to the 4x. Both of these you could do a u substitution for. If you had really wanted to, you could have said, oh yeah, we're going to let u equal 6x, du is 6dx, 1/6 du is equal to dx, and then have rewritten this as the integral of sine of 6x times du, sorry, cosine of 6x, apologies, times 1/6, and then integrated it and gotten sine of u. I'm trying to do too much at once. Apologies. Because that's 1/6 cosine of u. That looks terrible. Wow. Can you read that? Probably not. Maybe. Can I scribble more? Sure. And get 1/6 sine of u. And then end up getting that. You could do that every time for this. I really, really, really don't want you to. Okay, I don't not want you to. I don't want you to have to spend the time doing that. I want you to be able to be like, okay, I see this thing. I'm just going to divide by that coefficient because that's what happens every time. Because we want to save our time and energy for the more complicated things where we actually have to do a u sub and do the whole thing out, or actually have to do something else more complicated. So let's look at something like, sure, something like the following. The integral of, I don't, leave yourself enough room, James. Gosh, that's not going to go well. Something like the integral of cosine cubed x times sine of x dx. So there's some guidelines for powers of trig, for powers of sine and cosine. For powers of sine and cosine, there's a few different cases, but in the case where they're both odd powers, they're both odd, we're going to let u equal the trig function that's to the higher power. So in this case, which one's raised to the highest power? Higher power, cosine or sine? Cosine. So we're going to let u equal cosine, not cosine cubed, just cosine. Because again, we're kind of thinking you want to pick the thing that's stuck. In this case, cosine of x is kind of stuck inside being raised to the third power. So if we let u equal cosine of x, our du is negative sine of x dx. And I guess if we do it this lovely way you're doing in class. Sorry, I'm still obviously I don't like doing it this way in case I hadn't made that abundantly clear, but it's totally fine. I'm just biased. So this is going to equal cosine of x cubed is going to be our u cubed. Still have that sine of x there. And then dx is du over negative sine of x. So those end up dividing out to 1, and you're left with a negative integral of u cubed du, which is nice. It's just negative u to the 4th over 4, which is plus c, which is equal to negative cosine of x to the 4th over 4 plus c. And my bet is that your teacher probably hasn't talked about when one power is even and one power is odd, or probably isn't going to, but I'm still going to show you one example because I think it's worthwhile. So let's do another one. Let's say we have any more room. These aren't worthwhile, even if you're not doing the class. Let's say we have the integral of, sure, sine to the 5th of x times, sure, cosine squared x dx. Okay, so if we have one even, one odd, what do? You let u equal, oh, I have to think about it. Which one do we do? Okay, yeah. You let u equal the one that's even. Now, this might get in this. Oh, this is going to be terrible. James, you pick this problem. I'm going to change it just to make it slightly less terrible. Let's change that 5 into a 3. It already looks like a 3 almost anyways. Let's make that a sine cubed of x times cosine squared of x. Sorry if you make your 5s very nice and they look not like 3s. Well, it's a good lesson to learn. Make them look like 3s. Still the same idea. We're going to let u equal the trig function being raised to the even power. Now, here's the general kind of gist with this kind of problem. You're trying to make a choice for u so that after you deal with du, your du is still going to be just like before, negative sine of x dx, du divided by negative sine of x is equal to dx. So after you've made your choice for u, if you have any of your not u's left over, here's what I mean. We write this out, equal to the integral of sine cubed of x. Cosine squared is going to become u squared, and du over negative sine x, okay. That's going to take care of one of the signs. How many signs do I have left over? 2, or to a second power. As long as the thing that isn't u, right? So we chose u equal to cosine, sine is the other one. As long as the not u choice, as long as the leftovers are to an even power, you're in a good spot. So that's going to be true whether you're dealing with sines and cosines, or whether you're dealing with secants and tangents. or cosecants and cotangents. If the not choice for you has an even number left over, you're in a good spot. Here's why. Let's see, cancel one of those, cancel that one. I've got negative integral of sine squared of x times u squared du. I know a trig identity for sine squared. So do you. Cosine squared x plus sine squared x equals 1, or in this particular case, sine squared x equals 1 minus cosine squared x. But cosine of x is what we chose for u. So our sine squared x is really equal to 1 minus u squared. So that's the idea. You want a leftover even power so that you can use a trig identity to replace it with what you've chosen for u. It's kind of weird. It's not that weird though. This is going to be negative integral of 1 minus u squared times u squared du. Then we distribute. We get negative integral of u squared minus u to the 4th du. If you're me, you would probably do this and say, well, that's just the same as the integral of u to the 4th minus u squared. Distributing the minus sign and changing the order of, I mean, that you don't have to do that, but it's kind of not terrible to do. And then finally we integrate. We get u to the 5th over 5 minus u to the 3rd over 3 plus a constant. And then we plug back in what u is equal to, and we get cosine to the 5th x over 5 minus cosine to the 3rd x over 3 plus a constant. My gut is you probably won't see this in your class though. You probably won't have a leftover even power. So I'm not going to do more examples like this for now. And then there's the last case of sines and cosines, which I also feel like we probably don't need. Well, we can talk about this. So if all the powers are even, we're sad. I'm sad when all the powers are even. So if you have an even, both even powers, we'll go with the simplest example, the integral of sine squared of x. Oh, this is what I was thinking of. So I will point out, some people do something that I think is kind of crazy. Some people see this integral and they do integration by parts, which you totally could do. It's kind of weird in my opinion, but let's check it out because it's kind of neat. So in fact, let's check it out because I don't really know how it works, to be honest. I mean, I know how it works. Like I know how to do it. I just don't, I've never done it that way. So some people do this thing like, okay, well, I'm going to pick u equal to sine of x and dv is going to be the rest, which is also sine of x. Seems totally fine, I guess, maybe. Let's find out. Du is going to be cosine of x dx. V is going to be the antiderivative sine of x, which is negative cosine of x. Not dx, no dx, boo. Okay. I don't love this at all. This really like makes me unhappy. But we're going to get u times v. So negative sine of x times cosine of x minus the integral of v du, which is negative, yeah, cosine x times cosine x. So here's what you could do one of two things at this point. You could either do it again, and you probably end up back with sine x again. Or you can be sneakier about it and just use the trig identity right now. You can say that's going to give me negative sine x times cosine x plus the integral of cosine squared of x. We just talked about how cosine squared x is equal to 1 minus sine squared x. So what we really have is that the integral of sine squared x on the left is equal to negative sine x cosine x plus, I'm going to break this up into two integrals, the integral of 1 minus the integral of sine squared x. I'm going to add this to both sides. This is definitely never the way I would have done this. I'll just tell you. I'll show you guys the other way in just a second. And you can make your own choice about what you think is better. So anyway, doing this, we get 2 times the integral of sine squared x is equal to negative sine x cosine x plus the integral of 1, which is x. Finally, divide both sides by 2. So you end up getting negative sine x cosine x plus x all over 2 plus c. Super funky. Never done that before. It's kind of weird. Let me show you what I think is the more normal way of doing it. The less weird way of doing it. I don't know. Certainly the faster way of doing it. Let me show you the faster way of doing it. Don't worry, I'll still try to leave this easy. So, alternatively, you can use a trig identity. Okay, well, we just did, but I mean, a different trig identity. So, another way to do this problem is to say it's going to be the integral of, so here's a trig identity for sine squared. It's like the half angle identity, 1 minus cosine of 2x all over 2. That is another way, that's another trig identity for sine squared. Kind of weird. And then if we integrate that, well, let's bring out the 1/2. 1/2 times the integral of 1 minus cosine of 2x. So I get 1/2 times the integral of 1 is x. And the antiderivative of cosine of 2x is going to be sine of 2x. What else do I need? Yeah, division by 2. Now I should ask everybody, are these the same? They don't look exactly the same, but they are the same. And then the same once you recognize that sine of 2x has another trig identity. Trig identities for all the time. I get 1/2 times x minus sine of 2x is 2 sine x cosine x. And then the 2's cancel, and you exactly get the same answers you have up here. 1/2 times x minus sine x cosine x. Let's see. So this is the way I've always learned how to do it. It's the way I think you should do it. Again, what I should probably say is you're probably not going to see, I don't know. I don't know what your teacher is going to do. There's certainly not a problem like this on your homework. So I still feel responsible for showing you the thing. So I'm still going to show you the things. Well, let's move along. How much time? Oh, let's move along to 5 more minutes. Okay, 5 more minutes. There was definitely something, I'm sure. Yeah, let's get to these two. These two are important. So there's definitely 2 things on here that you need to be aware of. One of them we've already kind of talked about. So here's what I would say very generally about these trig integrals. If you're not sure what to do, often writing it in terms of sine and cosine is a good thing to do. So for example, if I was trying to integrate cotangent of 5x, and I didn't know how to do that, because honestly, it's something you eventually just memorize, or you can always do the thing we're about to do. If I don't know what to do, I'm going to go to cosines and sines. So I'm going to say, well, cotangent I know is cosine divided by sine. Specifically, cotangent of 5x is cosine of 5x divided by sine of 5x. So we're going to do a u sub. And we're going to pick u to be the thing that is stuck. U is going to equal sine of 5x. My du is going to be cosine of 5x times 5 times dx. I changed what we got to multiply by the derivative of the inside piece there. So there's a 5. Yeah, so I'm going to say 1/5 du is equal to cosine of 5x dx. And there's my cosine of 5x dx. So that's equal to my 1/5 du. This is going to equal the integral of 1/5 du over u. And you can break this apart or not. Some people are really uncomfortable with saying the integral of du over u is the natural log of the absolute value of u. So you can either write this as 1/5 integral of du over u, or if you prefer, 1/5 the integral of 1 over u times du. Whichever way you need to write it to make sure that you see that once you integrate it, you're going to get 1/5. The integral of 1 over u is the natural log of the absolute value of u. And so We get 1/5 the natural log of the absolute value of sine, apologies, of sine of 5x. More generally, this is something I think you all should do on your own. So you can show by doing the same sort of thing, the integral of cotangent of x is indeed the natural log of the absolute value of sine of x. And similarly, the integral of tangent of x is equal to the negative natural log of the absolute value of cosine of x. I will also point out, because it is something people do, some people prefer to write this as its equivalent, which is the positive. No one writes the positive part. I'm just trying to be emphatic here. The natural log of the absolute value of secant of x. And really, these are the same, because all they're doing is they're using a log rule and saying, bring that -1 up as the power, and cosine of x to the -1 power is the reciprocal of cosine of x, which is secant of x. So these two are the same, and people write either way. You could do a similar thing here. No one ever does. No one ever writes this as the negative natural log of cosecant of x. You totally could. I don't know why we don't, but we don't. Let me show you one last thing. It'll only take a second. The other one is, oh, come on. So you almost know all the antiderivatives of all the trig functions. The only thing that's left is secant and cosecant. And so to integrate secant of x, we do something really wild. Well, actually, the truth is, there's this other way of getting the integral of secant of x that involves using partial fractions, which we're going to learn about after this class. And then you do all this weird trig stuff. But it boils down to, we found out what the answer was, and then someone discovered a really slick way of getting there. So here's the slick way of getting there. You're going to multiply the top and bottom by something very, very special. I'm going to multiply by, I'm going to write this, yeah, let's do it by. So I'm going to write by, I'm multiply by tangent x plus secant x over the same thing. And then before I actually do anything, let's multiply at the top. So the top is going to be secant times tangent, which is secant times tangent, plus secant times secant, which is secant squared. And I'm going to reorder the bottom just because I want to. Instead of writing tangent plus secant, I'm going to write secant plus tangent. And now check this out. If we let u equal the denominator, secant x plus tangent x, our du is exactly the derivative of secant, which is secant x tangent x, plus the derivative of tangent, which is secant squared x dx. And look, that is exactly the numerator of that thing. So this ends up equaling the integral of du over u, which is exactly the natural log of the absolute value of u, plus c, which is exactly the natural log of the absolute value of secant x plus tangent of x. So it's kind of neat. You can find the integral of secant of x that way. And just as a kind of add-on, if I was going to find the integral of, say, secant of 3x, it would be exactly the natural log of the absolute value of secant of 3x plus tangent of 3x divided by everybody. Can't hear you. Thank you. Yes, 3. Exactly. Because if you differentiated this, you would get 1 over the stuff times the derivative of the stuff, and you end up multiplying by a 3 because of the chain rule. And then you divide by that 3 to counteract it. All right. That's all I got.